So, okay, guys. In any case, I will try to finish what I'm doing today and next lecture. Then Bjarne will come, and then I'll take some time off to regroup and figure out what we do, if we do anything at all. So you don't have long to suffer. Just 6 more hours of pain. Interestingly enough, I need to figure out whether to order more food for Bjarne's lecture, because some freeloaders might come.
Is there next or the week after?
That's the week after, 21st, I believe. So, but my today's decision is not to do it, because I'll just declare that people who never came before shouldn't eat free food. I think it's only fair. Do you agree?
No.
No? I should order. But how do I know how much food to order? But that will be encouraging people whom I don't want to come.
Well, you should announce that he's coming.
I did.
One more time.
Okay. So Paul is very kind, you see, unlike me.
You can have bouncers at the door.
Yes.
We can say that in the next lecture, coupons will be given out for free food during Bjarne's talk. So if you want that,
Well, or we could have a food fight. You know. All right, so what I'll start with, I made somewhat strategic mistake last time, which I'll quickly fix. I made 2 mistakes, and I'll fix both. One mistake was that I didn't have time enough to explain partition point at the end, and Param had some legitimate questions, doubting if it worked. We'll get to that. It does work. That is a second mistake. The primary mistake, again, if you remember, I told you that partition should first put guys who do not satisfy the predicate, and then the guys who do satisfy the predicate. But after sort of several sleepless nights, I decided that, yes, so it should, but it never will. The problem is that the standard does clearly stipulate that ones come before zeros. So ones will come before zeros for the rest of the course. So if Ryan will be kind enough, let's go to the file called search.h. So, and we will skip in the beginning there stuff which we don't need to look at, nothing changed there, and find the first mention of partition, which is partitioned. And as we see, now I changed it. How did I change it? It's a trivial change. Before, it was find if followed by find if not. Skip all non-satisfying, then skip all satisfying. Now we just changed it the other way around, all right? Which is what the standard stipulates, so it's a little change. So then we could go to partition point, and yes?
Should the names of those variables be changed to first true and first false?
A good catch. Of course, I was just flipping things, and yes, it works, except it's incorrect. Could you please, in both is partition, change the name of the variables? Thank you very much. Good catch. Obviously, I was not reading. And I did compile. Could we go to to the next version of is partition? I think it's needs to be fixed. That's true. Okay. So let us look at partition point, because it's as I said, it's probably the most important algorithm there is, or Paul's friend, should we tell the name? Paul allows me to disclose the name. Butler Lamson told us, remember I told you that there's only one algorithm needed, and that's binary search. So Butler Lamson believes that, so you better believe it too. So let us go and look at Butler's favorite algorithm. Okay? So these, of course, are flipped. Clauses are flipped since the last time, but the code is the same. And let us see Param expressed some doubts. And let us spend some time analyzing the code. First, a very important thing to remember, that whatever half is, half happens to be halfway, but it could be any other point. The range first n could be split in two adjacent ranges, first half and middle, where middle is moving first by half n minus half. Everybody agrees with that? All right? So, let us assume, now, let me even not, let us spend a little time on a simple issue of termination, not even thinking about what we do. We will think about what we do. Observe that if half is a positive integer greater than 1, specifically, then, well, if n is a positive integer greater than 1, yes?
Shouldn't I be a forward iterator instead of an input iterator?
Where does it say input iterator? I don't know why it said input iterator. I was drinking. We did it, I don't know. It should say forward iterator. Could you check? There shouldn't be any input iterators from that point on. What is the function? Do me a favor. Do you know how to do query replace?
Yeah.
Or something like query?
It should all be.
Yeah. Forward iterator. Thank you.
Not
Wait, it's not advanced speed.
No, not advanced. Advanced is fine. Okay, up. Let us just get upper bound. It's all forward iterated. It's okay. So everything is fine, except partition point. That's what happens, guys. Comments are not compiled. And yes, partition point. So let us look again at what is going on. So if n is greater than 1, which means that half is 1 or greater, everybody agrees with that? Then first middle is going to be a smaller range than first n, and middle and n minus half is going to be a smaller range. Do you agree with that? However, if n is 1, we have a problem. Do you agree with that? If n is 1, middle is going to be first, half is going to be 0, middle is going to be first, and n minus half is going to be equal to n. So the second subrange, so there is a possibility to be stuck there. Our code doesn't stack because we assure termination, because here on that path we reduce the second subrange. So we will always terminate. Now let's see why we terminate with the correct result. So, I mean, termination is good, but it's not necessarily the only thing we want. So, let us assume this is, again, a very important thing to remember. That if we know that a predicate returns false, let us investigate this clause, the second clause. It returns false. Now, our goal is to find a place which bounds the true guys. These are true guys, true, true, true. There's partition point, false, 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 false. Right? So if we find false, whether this false or this false, what we could say? Well, we could ignore all the guys there and just look at this range from C up to but not including F. Right? And that's, by the way, so let us do simple arithmetic. If we have KTs, our partition point is going to be at F plus K. Do you agree? If we have, let us do it one by one. If we have 0 T's, it's going to be F. If it's 1 T, it's F plus 1. If it's 2 T's, so everybody agrees with that? So it's F plus K. So if we look at the F plus K value, and it is K, we no longer need to consider all these guys there. We just need to investigate K guys to the left of F plus K. Again, the F plus K has K guys to the left of it, because we start counting with 0. This is sort of, and that's what we say here. We just adjust n to half to whatever we probed. We discovered that the false guy lives there. We ignore it. Right? Now, let us assume. Guys, this is really the most important algorithm. So, and as we shall see, it will lead to many, many other algorithms. This bisection is a very important thing. So this is the loop which you should learn by heart. So now let us see what, well, I didn't need to delete this guy. So we have true, 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 and then we have F, 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 F. And let us assume that we return true. Then our logic is the following. If it's true, it cannot be the partition point. Do you agree with that? Because partition point will either point to a false guy or to the last. So we could just discount everybody before and this guy too. So we're not discounting half guys, we're discounting half plus 1 guys. This is why we do that. We're discounting half plus 1 guy. You see here? It's plus 1. We probe the position half, but we could step one step ahead. And how many guys are left? It's n minus half plus 1. And what is first? First we need to, we could skip this guy. We put it right here. Well, or what, it doesn't have to be false, but we put it past the guys whom we checked. We no longer need to look at the guys before the one we checked and at the guy whom we checked. He cannot be the partition point. Is it helpful? Or you're still?
I'm convinced.
Okay. You were not convinced and you were right, in the sense we rushed through. And we basically waited. Go think, and you will figure it out. Which of course maybe you did. But nevertheless, I thought about it and decided that I absolutely have to show it, because this is so very important. Now, so, as I said, we are on the way. After all, Bartolomeo didn't say that partition point was the most important algorithm. He said that binary search was the most important. And the only algorithm. That was strong, the only algorithm. Right? So, and that is not binary search. So we need to find how do we get from this to binary search. And some of you thought about it, some of you didn't think about it. But let us look at the problem. The problem now, what we have, and here we need to talk about a little bit about something called a sorted range. Because a precondition to binary search is not is partitioned, but is sorted. Right? So, is sorted, again, we have a range, and it could be counted or bounded. The same, it could be given by, the beginning and the bound, or could be given by the beginning and the count, two ways. And then we know that range is sorted if it is, how would we say it mathematically? What is the property we're looking for? Monotonically increasing, and you would be wrong. Non-decreasing. Things are sorted when they are non-decreasing. Increasing is too much. If I want to sort my coins, and there are 2 pennies, however much I want to sort, I'm not going to have an ascending sequence of coins. Non-decreasing, it should never go down. So what we need to guarantee is that for no pair in general, this is true. This is my scribble indicating less greater than. That is never true. But that's too much to check. So here we need to rely on this amazing property that if we check adjacent elements and the property holds, then it will hold for all the elements. Why is it true? Transitivity at work. Right? This is again shows why mathematics is actually important. If you have non-transitive relation, it might not work. And you say, well, everybody assumes that. I could give you examples, for example, rather famous people who sort of do not quite get it. But, so we have transitivity. We have a requirement of weak streak ordering, which is transitive. So we'll be checking by that all the adjacent elements do not get it like that. And I decided that instead of bothering you with writing it, I'll just show you and we'll see if it works. The next function. I have a lot of stuff to cover, so the next function was partition point. Okay, so this is, do I need to explain this?
I think this is sufficiently explained.
Things are sufficiently explained. So if you want to do partition point with bounded range, find its length. In other words, you really cannot get to the middle unless you know the length. Okay, so is sorted. There are multiple things, and here I just want to allude to somebody who wants to study things, and all these algorithms are worth deeper study than we could do in class. There's an STL function called adjacent find. And there is a profound relation between is sorted and adjacent find. But you're going to discover the profound relation yourself. And in the class, let us just see how it all works. So, first of all, we know that an empty range is sorted. Then what do we know? That as long as we didn't reach the end first, and we didn't find a counterexample, we're not suddenly decreasing. We could go on. Do you agree with that? We could just, if we can go and we're not decreasing, we will go. So we reach somehow this loop terminates. So is it sorted or not? But the claim is it depends on which clause got us out. If we reached the end, we are sorted. If we didn't reach the end, somebody stopped us. Therefore, we're not sorted. Everybody agrees? Therefore, we just return this. Right? Now, here we go into this infinite thing when you design a library for yourself, for your friends, or for the world. Provide all the versions. So if it's sorted like that, you provide a version where you don't need to pass the relation. And what should it default? Again, there is a natural thing that it always has to default to less. Why? Okay, let us go through it again. Because in general, there are 4 possible choices, yes, for the default. So, first of all, there was one choice which sort of forced upon humankind. Increasing is better than decreasing, it's more natural. 1 to 3 is more natural than 3 to what? Right? Natural numbers go up, not down. I mean, we start with 1 to 3, we don't start with -1, -2, So that choice was self-evident. Then, of course, there was a choice of whether we use less or less or equal, whether we use strict or non-strict version. And somehow, I mean, this one, I don't have a really sort of absolute confidence, but I made a choice, and this is throughout STL and now throughout other libraries, that less is the primitive one that will always require strictness. But you have to decide, because algorithm will look different. If this is non-strict, then this code is not correct. What should this code be if this were non-strict? Yes. And that's why we need to make this choice. And this is why we say weak strict ordering. The strictness is a precondition. Otherwise, the code makes no sense. So we need to provide this. And now, whether we like it or not, we have to provide two more.
Is sorted n.
Yes. We need to provide two more versions for counted range. This is sort of, again, if we lived in some future world, they would be automatically generated for us. You know, when AI would become a reality, you know, HAL will do it. Old people remember HAL. But HAL, fortunately, is around Mars. Is around Mars? What is it? Around Jupiter? Which planet? Jupiter. Thank you. So he's not available. So we have to write them ourselves. So Ryan will skip that. And now we are sort of, this is, it's the same. And skip one more. Right. And here we get, don't show the code, we get to think, how do we get from partition point to lower bound? So let us assume that we have a sorted range of something. We don't know what they are. And somebody important comes with an element called A. I claim, which of the same nature, which is these things have weak streak ordering, and A is an element of the same domain. So, he gives it to us. What I claim now, there are 2 points which A establishes on this sorted sequence. Not 1, but 2. This is sort of mathematically, without thinking how we find them, we say there are 2 points. Indeed, let us assume that these are integers, and A is actually 5. So 5 then finds 2 positions, 2 iterators in this sequence. Anybody wants to venture a guess?
The first and last place that it could be. So if you have repeated 5s in your list, they would be distinct. They could often be the same if you don't have a 5.
Yes, beginning and the end of the range containing 5s. That's how I put it. Which obviously could be an empty range. Right? But there are two things. For example, it could be 1, 2, 3, 5, 5, 6, 7. Right? Then 5 will give us 2 points. This point points at 5. And what's the second point? That points to 6, past 5. Of course, if these are 4s, let us make them 4s. 6 remain, the position of 6 remains the position of 6. What is the other one? The same. It becomes pointing to 6. It's an empty range. So, what is the property of, let us go back to 5. It's a little bit easier when we distinguish them. So instead of 4, let me put it 5. How could we describe the property of the first iterator?
Everything from first to lower bound is less than 5.
And that's not enough. That's not good. So everything from here to here has to be less than 5. This is good. But you see, if it's the only thing, then this pointer will work too.
And it points at 5.
Ah, that we cannot say.
And everything, it's going to something greater than or equal to 5.
That nobody else is less than 5. We have a dichotomy. Everybody is, everybody to the left is less than 5, and nobody from him down is less than 5. Why is it good? Why am I happy?
It's a partition.
It's partition point. We reduced the problem. We no longer, you see all these things. This is why we don't want equal, because equal is a killer. Because there might be 5s in the sequence, or there might not. And then it comes all this badly designed binary search, which would return -1 when 5 is not there. Because they're always looking for 5. And it's not good. So, by the way, let me now disclose, these are the names, as far as I could ascertain, invented by me. But I think they are good names. There are 2 points, and I thought to call them upper bound and lower bound. This is, of course, is lower bound, and this is, of course, upper bound. Is the upper bound. Right. So what is the predicate? Now, just not rushing. So what is this condition? What is upper bound? Say it in English.
Everything from upper bound to the end is greater than 5, and nothing else is greater than
It's the first item that's not less than or not less than 5.
It's the first element which is greater, not less or equal. It's equal. Is the first. Okay. Now, in both cases, guys, we made a mistake. Because we always said it's an element which is less, it's an element which is less. It's not strictly speaking true.
Because there may not be an element.
Because it might not be an element.
That's why I carefully phrased it as everything in the range.
Yes. So, what we need to say here, that everything in the range from here to upper bound is not less or equal, which is, right? And everybody in this range is greater than. Of course, both ranges could be empty. Do you realize that? I mean, this both lower bound and upper bound split our range into 2 ranges. So in some sense, we have 3 ranges. We have the original F to L. Then we have yes, but I have to write it like low and high, because if I use L, there would be an unfortunate thing. And then I have upper, right? So there is a range from F to lower, from lower to upper, from upper to last. And all 3 ranges could be empty. Actually, all of them could be empty. Any one of them could be empty. It's a well-designed thing. It always returns. So let us look how we do it. This is, okay. And there's something, by the way, I need to say, but we will not do in the class, because I really want you to think about it. Because I don't really need it So that we have two functions, yes? Lower bound and upper bound. But STL actually provides another function. Sometimes, actually not as often as you would think, sometimes you need both. And you could find both a little faster than if you find one and then the other. So there is a function called equal range. Anybody wants to guess what it returns? Yes. It's pair of this and that. And now there is an embarrassing function. So I worked on STL, and if you remember, there was this grand review when they threw away lots of useful functions. But then they inserted some functions, very few. And one of them was a function called binary search. There was a conversation where my opposite number, let him remain nameless since he's a very good friend of mine, so this opposite number says, but where is binary search? And I say, well, there is upper bound, lower bound, I explained all of that, equal rate. And he nods his head and said, but where is binary search? So I said, that's binary search. He said, no, we need binary search. And I said, so what kind of interface would you like? He said, oh, like normal binary search interface. You give it a range and an element, and it returns true or false, whether it's there or not. There is a function like that in STL, because who would argue with the best friend? So, is
Not
it?
even null or non-null, just true or false.
It returns true or false. Yes. That's what I mean. Have I ever used it? No. Will I ever use it? No. Yes.
I use it.
Okay.
For set
Good.
membership.
For set membership, yes. But
I just used it for membership.
yes, one could use it. The problem is that I typically, if I want to find something, I usually want to do something with it. And this true or false returned to me are not really particularly useful. Right? I want to find, do we have a person who knows Python in this room? I go find param, but I need not just true or false, I actually need param, typically. So whatever. There is a function. It is, by the way, implemented with the help of, guess what? Lower bound. It's not a separate function. It's just a wrapper. I have to say something about students. Look, I have scars all over my body. So I earned it. This is why I wear long pants and shirt with. So, but sometimes a tie. You remember. Okay, so in order to obtain these functions, lower bound and upper bound, we need to write, again, we could do it, I am sure, with the help of lambdas and things like that. I actually find it much easier to write them explicitly. Because let us see. So I have lower bound predicate. And what is the lower bound predicate? It finds something, I mean, it stores pointer to A. By the way, anybody knows why it stores pointer to A and not A? Because I want to avoid, in general, algorithmically speaking, it would be silly if binary search-like functions would copy something. So this is why I take the references everywhere and then convert it into pointer. So hopefully the compiler will eliminate all of this and just go directly for the thing, and it actually does. So what I have is a low bound predicate, which takes, to construct, it takes our relation, and it takes some pointer to A. And when you apply it, it returns whatever this relation, x, and whatever A. Because we're going to, it's going to be true when things are less and false otherwise. Remember, our partition point right now is on partition things, true, false. And then, lower bound is a very, very simple function. First of all, there is a precondition. It requires that it's sorted. I do need iterated traits to extract whomever lives in this sequence. That's our magic implementation. But then we don't write any code. It's just partition point with this predicate. And then, sadly enough, we need to provide infinitely many versions. Right? Sort of. Let us just figure out how many versions of just lower bound do we need. First of all, we need to default R, which will default to less. Then we need to replace our counted range with bounded range. By the way, the standard, as far as I know, still does not do things like that for counted ranges. They introduced some counted ranges, but for this one, where it is actually absolutely essential, as we shall see for coding, that's above the pay grade. So there's still no lower bound n. Probably 12 years from now, you'll get it.
But is the one that you do have, does it use getting the distance between the iterators?
Pardon me?
Does the lower bound, you pass it first, you pass it last, does it use distance between?
Yes, it does.
Okay.
So it will work. The problem is that it will use distance all the time. If you know n and you have 4 iterators, you're going to be doing this extra pass overs, which is also very unfortunate. We'll see the code in 15 minutes. Or after lunch, let's say after lunch. See the code. So remember, we're just doing all of that to learn to do merge, in order to do merge sort. And so what it has to do with anything, well, we'll find out. So,
I have a question.
Yes.
Is partition point, is the guarantee on the forward iterator that it only does
log n application of the predicate.
well, log n application of the predicate, but how many
N minus 1.
n minus 1 possible increments?
Yes.
Right.
We discussed it last time.
Okay.
So, because
It makes sense.
it does, in other words, it does. Simply speaking, I'm counting ones, but it does n over 2 or n over 2 minus 1, n over 2, n over 4, n over 8, n over 16. And when you add the top, it adds to n, actually n minus 1, plus you lose a bunch of ones. It could be good for you. It could be n minus log n, actually. But n, simply speaking, n minus 1 is the number. But, so, partition point, but making them is a mechanical thing. It takes literally a few seconds. It takes decades to put them in the standard. Writing them takes seconds. So let us look, for example, in order to do bounded version, going to first last. I don't need a new algorithm. I just need to say first distance and r. And again, I do need to, I mean, there is no way, I repeat, to do binary search without knowing the distance. Because you need to know half of the distance. You cannot know half of, I mean, there are people, actually, there would be somebody clever say, oh, but I could write a piece of code which gets to the middle without knowing the number. I can do it too. What you do, you have 2 pointers, one does 2 steps, then 1 step, and when the second one hits the end, this one will be at the middle. It's an expensive way of doing things. So low bound, let us go, and then this low bound n defaults to this, and so this is a mechanical thing done with cutting and pasting. Again, I'm not, guys, the point here is not that somebody will say, oh, Alex just talks about his beef with the standard limit. No, what I'm trying to tell you is that when you write things like that for your code, that when you come up with an algorithm, see all the, I mean, there will be some other guy using your code. You should always think about the other guy. This is the great mistake, the great flaw in most codes I see, is that it has no consideration for the other guy. Right? The idea is that I'll write this code, it works, whatever that means, and this is done. Right? There is no consideration for the guy who will attempt to do something else so that he would inherit a usable artifact. Right? So my dream is that all of us would be writing code thinking of the other guy, right? Not just of my task. And say, well, but then I have to do more work. This is the beauty of sharing. Some of you might have attended kindergarten. But remember, you had a very nice teacher, and she told you that it's good to share toys. She was right. It's actually good to share toys. If we all would think about the other guy, if instead of just thinking what I need right now to get a raise, I'll start thinking about solving the problem and maybe even getting a raise, but then Ryan could use my stuff. The world will be a better place. It goes along like, you know, when we use the sink in the kitchen, we shouldn't leave dirty dishes in there, as it says so, but people still do. We shouldn't do it. There should be this consideration in programming as well, not just in the kitchens. We should try to, I should try to make an effort and write all 4 versions. Even I need one. Ryan might need the other one. He might not want to say, oh, that's all right, he will call distance. He doesn't have to call distance. I'm allowed to dream. That's everything.
And multiple versions isn't even the most difficult thing about sharing. Right? The difficult thing is to, first of all, write an algorithm that is fundamental in the first place, to even allow.
Yes, all of this. Of course.
This is trivial after that.
Of course. So the most, and I hope that's what I'm teaching you. Discover this out. I mean, again, I have arguments. People say, well, you have to teach them use things without not write them. I actually don't believe that. I think that the only thing I could teach is how you produce components from scratch. And I just use my simple examples, instead of coming up with some examples. I mean, we did a whole bunch of things not known to me, but this one was known to me. Okay, so upper bound would have an upper bound predicate, which does this thing. It will return not, well, it will do the right thing. It will skip all the guys which are either less or equal. Right? It will return true. And we do not need to see We will see that. We will see. So just let us go because we need to get to merge. So we have all the versions of upper band. Okay? So try to, if you have time, try to do equal range. It's an instructive problem. Whether you could do, obviously there is a trivial implementation. But could you do better? You understand why you should be able to do better. You see, the first time you poke, already you could use them both because. So, all right, guys, let us go. They already have some kind of food for us. We will eat it, and then we will start working on merge.